Hi, Astronomy. Mr. Janowski here. This is part 3 of the chapters 14 and 15 slides. So in the first part, we talked about, the life and evolution of low-mass stars. In the second part, we talked about the life and evolution of high-mass stars. And now we're going to go back and look at all of the different stages um, in greater detail. So we're not going to do all of the stages in this part, but we're going to start looking at the different stages and get a better sense of what's going on in those little stages. So let's get started with that. So what is the dividing line between high and low mass stars? Oh, I meant to hyphenate that. I forgot again. The dividing line between high and low mass stars is about 8 solar masses. So according to our models, if the star has up to about 8 solar masses, we consider that a low mass star, and its life will be a certain way and its death will be a certain way. And if it has greater than 8 solar masses, then it's a high mass star, and its life and death will be a little bit different. So which type of stars live longer, the high mass stars or the low mass stars? Turns out the low mass stars actually live longer. So even though they have less fuel to burn, they do so at a slower rate. So again, here is the luminosity and mass relationship. So the bigger the mass, the more luminous the star is by a lot, because luminosity is proportional to mass cubed. So that means if you have a star that is 8 times the mass of the sun, so this is right on the border between low and high mass stars, it has 8 times as much fuel, basically, but it's 512 times as luminous, which means it's going through its fuel 512 times as fast. So what kind of corpses do low mass stars leave behind? Low mass stars leave behind white dwarfs. So this is the ultimate fate of the sun. The sun's not going to explode. It's just going to eventually kind of lose its grip on its outer layers and drift apart and stop doing fusion. And what's left, the corpse of that star, will be a white dwarf. And, oh, well, that's definitely a typo. The other question is, what kind of corpses do high mass stars leave behind? High mass stars leave behind either neutron stars or black holes. So lower mass, high mass stars, so 8 to about 20 solar masses, will leave behind neutron stars, and 20 solar masses or more will leave behind black holes. So, yeah, if I remember, I'll go back and fix that typo. I bet you the same typos on the previous slides, too. Too much copy pasting. So there's a quiz on Google Classroom. Clearly, you don't actually have to take it, but it's there if you want to, just to check your understanding of this. And I don't know why I made, 2 separate slides with this idea. But yeah, there's still a quiz on Google Classroom. Here are HR diagrams and the life cycles of low and high mass stars. And there's a Kahoot. So I'll put a link to the Kahoot in the description of this video. And if you want, you can play the Kahoot. So before we start doing the words, this is a interstellar gas cloud. It's fun to look at clouds and see, the pictures that you can see. So take a look, see what kinds of things you can see. I have always been convinced that this is like a demon. So if we look, we can see the demon's eyes and his nose and his mouth and even his pointy chin. And so one way I think of this is like, okay, so here's the demon, and you can kind of see the demon dancing. So he's got his right arm going up like this, his left arm like this. He's standing on his left foot. He's got his right foot up in the air. Other people have said they see an elephant. So here's the elephant's trunk. Here are the elephant's eyes and the elephant's ears over here. And so maybe you can imagine we've got a demon, not a dancing demon, but a demon riding an elephant that's charging towards us. So that's what I see in this cloud. Maybe you see different things. But anyhow, the first part of a star's evolution, before it's even a living star, it's going to start off as an interstellar gas cloud. So these are huge clouds of gas and dust that orbit inside of our galaxy. So by mass, the gas is about 71% hydrogen and 27% helium. So that's about the ratio of the regular matter in the universe. It's almost 3/4 hydrogen. It's about 1/4 helium, and there's very little of everything else. And what's the dust? So it's not like household dust. Dust, what astronomers refer to dust, it's actually solid microscopic particles made primarily of silicates, carbon, and iron compounds. So hydrogen and helium, they've been around since the Big Bang. Where did these other things come from? Well, remember, at the end of a star's life, it either drifts apart if it's a low mass star, or it explodes in a supernova if it's a high mass star. And in either of those cases, all of the things that were in the star just kind of drift off and become a gas cloud. So this is not, the gas cloud we're looking at would not be a first generation gas cloud. This would be one that's made of gas, gas and dust rather, that was previously in other stars that died. So yes, circle of life. So the clouds are usually very cold, only about 10 Kelvin. So if we go back one slide and look at this picture, this is the picture that was right out of the textbook. So this, clearly looks like fire, so you would think this is very hot. But yeah, this is a radio image, so this is not even visible light. This is a false color image that's made to look red, and it looks very pretty. But in this one, I changed the color, so you get more of a sense that it's actually, it's not very hot. It's actually only 10 degrees Kelvin above absolute zero. So remember this. This is the ideal gas law. And in the ideal gas law, it relates pressure, volume, and how much, the number of moles or the number of particles you have, R is a constant, and temperature. So basically, in this case, we're interested in the relationship between pressure and temperature. So if this cloud of gas is only 10 degrees above absolute zero, it's got a very low temperature. That means there's not a lot of pressure pushing outward. So ordinarily, a cloud, at regular temperatures that we're used to dealing with, is not going to collapse under gravity because there's too much pressure in the cloud pushing out in all the other directions. But if this cloud is this cold, there's very little pressure to prevent gravity from bringing it together. So eventually gravity will start to make this cloud collapse. And again, sometimes this is spurred on by this cloud colliding with another cloud or a nearby supernova sending a shockwave through the thing and kind of crushing it up a little bit. But yeah, the big idea is there's not a lot of temperature. There's a very low temperature, so there's not a lot of pressure to prevent the collapse. So down to here, these clouds are not uniform. So it's not a very even distribution of gas. Like you can tell in this cloud, there's a lot of gas in this area, and there's very little gas over here. And some areas just seem denser than others. So the stars and the solar systems, as it turns out, are going to form in those clumped areas where you have more density, where you have more stuff. And because of this, stars tend to form in groups at approximately the same time. So if we see these little clusters of stars, one thing we can generally assume, at least according to our theories, is that if you see a cluster of stars, they're probably all about the same age because they probably all formed at about the same time from the same enormous cloud of gas. So a dense clump of gas within a cloud will begin to collapse due to gravity, which compresses and heats it. So yeah, gravity brings everything together. You start getting friction from the particles colliding, and the thing starts to heat up. And now the idea at the bottom, any rotation the cloud had before it collapsed will be conserved, flattening the cloud into a disk like a tossed pizza dough. So this is called the conservation of angular momentum. So if you remember the fun thing we did back near Thanksgiving with the spinning chair and everything, that's the conservation of angular momentum. And this is what I love about physics is, that idea that we did in the spinning chair, the exact same thing is what forms stars, and it's what forms planets and solar systems and everything like this. Just like the figure skater can bring her arms in when she's spinning and she'll start to spin faster, but she keeps all of the angular momentum she had at the beginning. The same thing happens with this giant cloud of gas. So it starts to collapse. And if you've ever seen, a real pizza being made, the pizza guy is going to take the pizza dough that was originally a ball, spin it, and centrifugal force kind of flattens it out into a disc. And the exact same thing happens when this is going to be a protostar, when a protostar starts to form. So whatever angular momentum was in that cloud when it was big and loose, as gravity starts to collapse it and tighten everything up, it's going to start to spread out like this into kind of a disc shape. And within that disc, where the most mass at the center is, well, that's going to be the star. And if you happen to have little clumps of stuff that are more dense than others out, towards the, in the sides of the disc, those little clumps eventually are going to form the planets. So, look at the picture of the guy throwing the dough up in the air. And that's very much tells you the story of how the sun and the earth and all the other planets formed. That's also why all the planets If we think about the elliptic from way back in astronomy, not the elliptic, the ecliptic, um, this is why all the planets rotate in approximately the same plane, because we were all in the same flat pizza dough at the beginning. So after a million years or so, the disk forms a small hot dense core at its center, and we call this a protostar. So protostars are about 1500 Kelvin. So they shine mostly in infrared. So 1500 Kelvin seems hot compared to day-to-day temperatures, like room temperature is about 300 Kelvin. So this is fairly hot, but it's not hot compared to a star. So in this star, we don't actually have hydrogen fusing into helium in the core yet. So it's getting hotter because everything's collapsing, but it's not technically a living star yet. So if we think back to the Wien's law picture, so the coolest image we have here is 29 Kelvin. I'm sorry, 2900 Kelvin. So if we were looking at 1500 Kelvin, that peak's not shown, but it would be a very low, broad peak that peaks right around here, 1500 Kelvin. So in this image on the left, we have the pillars of creation. This is one of the more famous images that Hubble has ever taken in visible light. And yeah, it's a beautiful, fascinating picture. And the pillars of creation are part of what's called the Eagle Nebula. And I've never been sure what exactly the eagle is. So are these three little pillars, are two of them the wings and one of them the head? And is this the head and the beak and the wings are out in front of the bird? Or is this the head and the wings are out on the sides? I don't know what's going on. But anyhow, so yeah, this is the pillars of creation in visible light. And this is the same image in infrared light. Now, it turns out in visible light, all that dust and stuff is going to block most of the visible light. So that's why these pillars look, vaguely solid. But when you take it in infrared, which is longer wavelength, the longer wavelengths of infrared light mostly go through the dust. So you can see a lot more of what's going on because the light's not getting blocked by the dust. So yeah, this is a false color image in infrared. And you can see many of the protostars that are starting to form inside of all of this collapsing gas. So it's up to you which one you think is the prettier one. I mean, this is certainly the more famous one. But yeah, this one is kind of really, really cool looking too. So protostars often eject gas in bipolar flows. So what that means is if we're looking here, this would be the, where the protostar is. And this is light that's shooting away from us, so they made it look a little redshifted. And this is light that's shooting a little bit towards us, so they made it look blue shifted. And they're not actually sure why we get these bipolar flows. So it's a running joke in astronomy that whenever something comes up that you can't understand, you kind of attribute it to magnetism, because magnetism is really complicated. So yeah, why does this protostar not just, so the pizza disk would be going out like this, at this angle across the whole image, and then kind of right up and down through the pizza dough, you have these flows of material that are being ejected outwards. And why? Well, we don't really know. So let's just say it's magnetism is causing this somehow. Works for me. So here we're looking at a young star cluster, NGC, New General Catalog 2264. And here we're looking at the HR diagram, the Hertzsprung-Russell diagram. So we've got luminosity going up here, and we've got temperature going this way. So this is an example of an HR diagram that is not of all the stars in the sky. They're just using an HR diagram to kind of analyze what's going on in a particular region of the sky. So this particular star cluster. So we've kind of caught this star cluster in the middle of what it's going to do. So it has formed some of the stars already, but it hasn't formed all of them. So what happens is the more massive clumps, well, those form the more massive stars. And because there's more mass there, they tend to collapse more quickly. So those more massive stars, the blue ones, have already formed and they finish contracting. And those stars are on the main sequence. So if we look at this HR diagram, these are the hot ones. So these are the big blue ones that are here. And the less massive clumps are kind of in the middle of forming their stars. So these are still protostars. So they haven't joined the main sequence yet. So I don't know why they're being shown out here. I really don't see why they would be coming from above. They would seem to be cooler and less luminous. So these guys should really be coming cooler from over here to the right and way less luminous, so from below. But in this drawing, I personally think this is probably a mistake in this drawing. But anyhow, yeah, sometimes you'll see a star cluster, and all of the stars have formed at this point, and you'll have blue ones and the red ones. This particular one, we've only caught it halfway through. So the more massive ones have already finished forming, and the less massive ones are still in the process of forming. So, last chapter we learned that most stars fall within a fairly narrow range of masses. So, remember, stars vary tremendously in terms of their size, in both their radius and definitely in their volumes. But mass wise, they're not all that different. So, most of them are within what we would say an order of magnitude of the mass of the sun. The sun has one mass of the sun, is the sun's mass. And your least massive stars are going to be about 0.1 times the mass of the sun. And your most massive stars are a factor of 10, 30 is a factor of 10, more massive. So first, the little ones. So if you have a star that is less than about 0.1 times the mass of the sun, so 1/10 the mass of the sun, you're not going to see many stars like this because these stars are so unmassive, there's so little stuff there, that they never collapse enough that their core gets hot enough to fuse hydrogen. So there's a little more detail to that. They can form they can fuse an isotope of hydrogen called deuterium, but they're not hot enough to actually form regular hydrogen. So they are actually doing a little bit of fusion, but not a lot. But never mind that detail. So anyhow, 0.1 times the mass of the sun. If the star is less than that, if the star in scare quotes is less than that, you have what's called a failed star, aka a brown dwarf. So yeah, here we get at the scale. So here's the Earth, here's Jupiter. So Jupiter is a big planet. The sun is a kind of medium-sized star. So this guy right here, this red-looking one, we couldn't call it a red dwarf. Red's already been taken. So we call it a brown dwarf. So basically what happened is a big gas cloud collapsed and tried to fuse, to get all its mass together. And it's trying to, get its core hot enough to do fusion, but there's just not enough stuff. So it can't squeeze hard enough, so it never actually achieves fusion. So instead, we end up with this failed star. So you can think of it as a failed star or a very successful planet, if you'd rather think of it that way. It sounds a little bit nicer. So yeah, it's bigger than Jupiter, but smaller than a star, and it's not massive enough to actually start doing fusion. So it's a failed star. It's a brown dwarf. So that's the low end. Now to the high end. It's rare to have stars that are more massive than 30 times the mass of the sun. So according to our models, this is has large a mass as a star should have, for the reason I'll get to in a second. Now, they do occasionally find ones that seem to be much more massive than this, and that's still a bit of a mystery. They have found stars that are like 300 times the mass of the sun. So maybe they're catching them just in their very, very brief lifetimes. But yeah, in general, it's very rare to find stars that are more than about 30 times the mass of the sun. So what's going on is, as this massive gas cloud is collapsing, eventually, it's going to heat up and form a protostar, and then it's going to start doing fusion in the core, and that kind of ceases the collapse because now we've got pressure pushing out. So it kind of limits how much stuff can fall in the star in the first place. But if you did have a more massive star than that, if you had a star that had about 200 times the mass of the sun, we'll plug that into the mass-luminosity relationship. So if it's 200 times the mass of the sun, it would have 200 cubed, or about 8 million times the luminosity of the sun. So this guy is burning so crazy, crazy bright that it's going to quickly shine itself apart. So maybe a metaphor for, I don't know what there. But yeah, it's burning too brightly, it's shining itself apart, and it's just going to rapidly blow its outer layers into space. So it doesn't seem like, occasionally they do find stars that are more than 30 times the mass of the sun, and some that are a few hundred times the mass of the sun. But those really massive ones are very rare. So, to review, what is the first stage of a star's life before it is even alive? Oh, I didn't animate these slides correctly. Look at this picture of the dancing demon, or the demon riding the elephant. That is a interstellar gas cloud. So what is the second stage, when the star still isn't alive yet? Well, after it's a gas cloud, it will form a protostar. So I'll go back. I'll fix all my typos, and I'll animate this slide correctly. Next review. This image I do want up here. So what's, no, I don't. Oh, damn. What's the lower mass limit for stellar formation? And what are failed stars below this mass limit called? Well, the lower limit, the least massive successful living star you can have, is about 0.1 times the mass of the sun. And if your star has less than that, it's not really a star because it's not hot enough to do fusion. So that kind of failed star is called a brown dwarf. And what's the higher limit for the mass of a star? It's about 30 times the mass of the sun. Again, for this reason, the luminosity mass relationship. So if a star starts to get more massive, it starts to get way more luminous much more quickly. So that means if you have a really massive star, it's going to basically shine itself apart. That's it for part 3 of the slides. Hopefully you found that interesting.